All right, everyone, welcome to the next discussion. So in the first problem, we're mainly trying to come up with an idea of quick select, but now for matrices instead of just arrays like originally. And we're going to break this down into a couple of pieces. So the first thing we're going to do is we're going to consider matrices M that are sorted in both their rows and their columns. So in particular, let's say you had the matrix 1, 2, 3. Clearly that's row sorted. It's also column sorted because there's really nothing going down the columns. And then we can make 4, 5, 6. So now the second row is sorted, but we also have that if we look at the columns, 1, 4 is also sorted, 2, 5 is sorted, etc. And we're going to require this pattern for our matrices. So not only is an individual row sorted, but the columns are also sorted. So that's the type of matrices we're going to deal with. And the first thing we're going to look at is counting the number of elements in a specified range. So we're given these indices I0 and J0, and then we're given a pair I1, J1, and we want to compute the number of entries of M that are larger than Mi0, J0, and smaller than Mi1, J1. So we drew our picture for M, so we have this matrix. This is our M. And let's say I0 is here, I1 is here. This is one of the rows. This is another row. Then we also have J0 and J1. These are the columns we're considering. Then the two elements we're looking at are this element and this element. And we want to count entries in this matrix that are larger than this element and smaller than this one. So clearly, if the rows and columns are sorted, we know that everything to the right of this entry will be larger than I0, J0, and so we should consider it. And probably these will also be included. So because it's sorted, we know this one will be smaller as we go down. So as we go down the matrix, we get smaller, and so these elements will all be satisfying the requirements that they're larger than this entry, but smaller than this one. So in particular, because we know it's sorted both row and column, we can immediately know that these entries will all be satisfying the requirements. So we know for sure we need these. So we will include these for sure. But we could possibly have some over here. So we know these are larger than the ones above them, but not necessarily how they relate to this entry here. So we need to somehow figure out how far we want to go outside of this box. That's kind of the idea. We want to somehow figure out, okay, how far to the left do we really have to go before we are actually smaller than the I0, J0 element. And so this is kind of the idea, and we're going to do this in a very simple way. So we're going to define for row K, so let's fix row K. And let's define SK to be the first element or let's just make it an index, so it's the first j, such that mkj is at least m I naught j naught. So you could think of it as far left as we can go in the row, while still correctly satisfying one of the two properties we need. So this is kind of like a left bound for row k. And that's kind of the idea here. This would be our SK, is whenever we finally hit something that's smaller than the smallest thing we should be considering. Similarly, we'll have LK, so for larger, and this will be the first J, such that MKJ is greater than MI1, J1. So intuitively, you want to think of this as the last J, such that MKJ is at most MI1, J1. You want to think about it this way, but because we're going to deal with like off by one errors, because we're counting lengths, we're going to prefer this definition. But they're essentially equivalent in terms of ideas at least. So if we have this, then the number of entries in row k satisfying at least m I naught j naught and at most m I1 j1 will be exactly the max of LK minus SK and 0. So we also need this extra case where SK will be n plus 1 if no J exists. And we'll have the same thing for LK. So this is the case when, nothing is actually smaller, and equivalently nothing is, or everything is larger, then we get these n plus 1 cases. And in general, when LK is at least SK, when this is the case, then we have at least one element satisfying the property. And so in that case, the max will be LK minus SK, not 0. But if LK is to the left of SK, then no elements satisfying the property. Either the elements are all too big or they're all too small. And so we get 0 total elements satisfying the properties. So then we can just sum from k equals 1 to n of this quantity. And this will be our final answer, and I'll call it Tn. And this is the final answer we want. So this is giving us the correct answer. Now the question is, how quickly does this algorithm work? So we want it to be O of n. We don't want to have to look at every single entry of the matrix, just a few of them. So the critical thing to notice is if we have our row 1, let's start with S1 equals n plus 1, and we'll loop from the end of the row to the beginning until we hit a position, let's call it H, and H is the first time where we go beneath MIK. So here we have M1H is strictly less than M1 or MI naught J naught. So H is the first such time, so in particular H plus 1 is safe. In fact, H plus 1 will be our desired SK. So then we know S1 is equal to H plus 1. So we can start with S1 equals n plus 1, and we continually go to the left until we find an element satisfying this property. and that becomes our S1. Now, we did that for row 1. How do we do it for row 2? It's going to be almost identical. So the key thing is, because this is sorted, we know that for row 2, this element for h plus 1 can only get larger. So M2 S1 is going to be at least M2 S1. So in fact, we only get larger. So if we're looking for the smallest j satisfying the property, it can only be towards the left of this element. So in particular, S2 will end up being smaller than S1. And inductively, this will always be the case. So Sk will always be at most Sk minus 1. And so what happens is we're doing this scan from right to left, but we only do it, we don't do the entire row. We only do part of the row, and then we do part of the next row, and so on. So in total, we're actually only checking O of n elements of our matrix M to compute all of the S values. And then similarly, we can do the same thing in the reverse order to get the L's. And then we just compute the sum, which is sum over n things. So overall, this is going to be an O of n time algorithm, as desired.